Become a sustaining member of the Commonwealth Club for just $10 a month. Join today.
Welcome to the Commonwealth Club. I'm George Hammond, Chair of the Humanities Forum, which organized tonight's event. We're going to be speaking with Stefan Alexander, a physicist, on his book, Fear of a Black Universe. And I'd like to welcome our online audiences, our live stream audiences, and those of you who listen later on YouTube or Facebook. And this is one of over 600 programs we've done since the pandemic began, and we are about to begin having normal programs at the club again soon. But in the meantime, we're here to discuss major issues in physics, which Stefan took on in his book in a fascinating way. So first of all, welcome very much to the Commonwealth Club, Stefan. And my first question for you is, I thought your idea in your book, about the middle of the book, about diversity, having diverse views, was tremendous because, I mean, there are basically millions of minds all attempting to have give ideas about what our shared reality is like. And if we don't take into account all those different viewpoints, I mean, it's rather hubristic of us in the first place to think that we can figure this out. But if we don't take into account all those different things, we're more shot than we are normal. So I wanted you to talk a little bit about that because I thought that was an interesting angle on your book.
Yeah, thanks. And it's a great honor to be here at the Commonwealth Club. Always been a big fan since my days living in San Francisco 20 years ago. So it's amazing how things come full circle. Man, you really hit the nail on the head with that question. Because I think yes, when we look at the history of science and the development going way back 500 BC with the Pythagoreans and even all throughout the world. I mean, we've had special individuals who have, been credited, and rightfully so, to make the big leaps, the big breakthroughs. And so, yeah, I mean, but as you said, there's a sense in which there's a part of me that realizes that as a researcher and as a person that teaches physics and, that there are times where I will get an interesting perspective and idea from a student or a beginner or someone who is green behind the ears, right? Mm-hmm. And I think that I put my flag on, put my flag down or whatever that saying is, and say that I do believe that we all as human beings endowed with the same, senses and all the things that we have as human beings. I think we all, as I said, we all have our experiences of this reality that we're in. And I think we should respect that and in that spirit, open a door. And what I'm saying, open the doors for others to also explore with us. And that's not coming from a naive kumbaya place, by the way. So I just want to also say that at that level. Yeah.
Well, I think it's important even to think, I mean, you talked about the Pythagoreans. Well, but Pythagoras traveled around and he had a whole bunch of Egyptian priests that he studied with, and then he went other places. And, maybe he got rid of 95% of it. But even if they just did things with intuition, there's still angles that they took that influenced his ability to put ideas together in a different way. And I think every great thinker who, as you said, is part of the recorded history, has at least 1,000 minds probably that they took things from. And I think it's important for everybody who wants to push the scientific thing forward to think, you don't have to be Einstein to make this happen. You can be somebody else that does some other research that then you just put it down, your piece, and somebody else looks at it, picks it up, and works with it later for a bigger picture thing. So that everyone feels, and they should, that they're a part of that operation that humanity is on. And as I said, it's kind of hubristic of us to do it, but we're making great progress. So we really don't need to stop.
Yeah, totally agree with that. Totally resonate with that.
All right, good. So let's talk about the three big issues in your book too. You said that in your book, you wanted to talk about three big things. One was intransigence, right? If I got that right. Oh, invariance, not intransigence. Yes. Invariance. And then, so why don't you talk about that idea for a little while? Why is that one of your important ideas?
Yeah. So it starts with, of course, it's, one of the things that attracted me to physics, I actually tried to be a biologist first. And then when I realized I had to take organic chemistry, I ran away. But I think the idea of the economy of, the economy of being able to explain many phenomenon with one set of one idea or one equation. And I think behind that is this, the search to find simple things, simple ideas. And through these simple ideas, then maybe, you have a whole web of complicated things going on. And boy, wouldn't it be great if we can just find some elegant, simple way of explaining all that complexity, where that complexity grows out of from this simple idea. And I think Albert Einstein, in his idea of principle theories, coming up with underlying principles that can encapsulate all, a wide range of phenomenon. And I think, he put when he realized that through special relativity and then later on general relativity, that the principle that seemed to encode that physics, time dilation, length contraction, all these zany, magical features of nature. The thing that was behind that was the idea of invariance. That so the idea, Albert Einstein put this principle at the forefront of physical law. And the idea, very simply, is encoded in an example. I give you a square. I put in a square sheet of paper. Well, let's do it. iPhone is not a good idea here. Okay, I got something on the old box here. Here's a square box, right? And then I tell you to close your eyes, and we will ask everyone to close their eyes. And some people are not, but clearly for those that don't, I'm going to do something to the box. And then you open your eyes, and it looks exactly the same. Okay, but actually what I really did was I rotated the box by 90 degrees. So the idea of invariance is that I basically do a transformation on an object, and I realize that the object looks the same based on that transformation. And so I call that an invariance. So the object is invariant. It looks the same even after I made a transformation. So therefore, we discovered that the box has this symmetry, which is rotation by 90 degrees, right? So what Einstein basically was saying is that, hey, maybe the laws of nature is like this, at least gravity, which is different. If I now assume a transformation has to do with moving an observer by a given velocity, and another observer is moving by a different velocity, that's a transformation. He said, there are some things that are going to be invariant, that does not care about how I transform or how I change things. So change in a physical system, there are some things that are not going to be invariant. They're not going to change. And that case was the speed of light, for example. Now, so the idea of the invariance principle, which underlies that in mathematics, are symmetry principles and how you transform things. So what Einstein basically realized was that is a principle of nature. And then the theory of general relativity then turns out to confirm that, because in general relativity, he's saying the laws of nature does not care about any transformation that you make of your frame of reference. Whatever the laws are, it doesn't care about that. And then if you formulate now the laws such that you figure a way of just mathematically making that statement, of course, mathematicians gave us the math. It's called group theory, amongst other things, that tells you how to do that. Then you find, bam, you get the theory of general relativity, and you get the curvature of space-time and all these beautiful features that we now confirm with the existence of black holes and gravitational waves. This invariance principle seems to be or symmetry, which is, I'm going to use those words synonymously, in a naive way, of course, to say that the laws of nature does not seem to care about the different perspectives that one takes, that the laws are somehow encoded, whatever the laws of nature are, they are encoded such that they don't care about these different ways of looking at things. And it turns out that actually, one last thing I'll say is that that idea led of invariance and symmetry also applied now to the other three interactions, that they themselves enjoyed symmetry principles of their own or invariances of their own.
Mm-hmm. Yeah, it's interesting to me from a philosophical point of view that Plato had this idea about eternal ideas, and that's an invariant idea as well. And it's similar in that he had some personifications involved in his things, but in the end, what we've done with that is we come up with the concepts, and we have this continuum of change. But what is, to me, uninfluenced by the continuum of change is what's invariant. No matter what the continuum of change does, there are some principles that don't change, like even like gravity doesn't change no matter what's going on in this case. But there are lots of other principles, like the Pythagorean theorem about triangles, and so on. There are just some things that don't. And it's interesting because it's a weirder word to use than invariance, but that's eternal. It's uninfluenced by change. And so it's so different than our other idea of eternal, which is heavenly and so on and so forth, where there's supposed to be plenty of change going on. It's just, this is invariant. And I think that's what Pythagoras hit on, among other things, that there's some things that just don't change no matter what you do. And that's where we should start trying to piece this puzzle together with, because it's going to be impossible to do it just on the flow, the continual flow. So that's number one. And then superposition is your second one, right?
Yes. But before you go on, I actually have a question for you, because it seems that one interesting thing that it's hard to incorporate into physics is the idea I hear from my friends in philosophy who say things like, well, the only one thing that doesn't change is change itself.
Well, they do that. The existence of change can't change if change is a continuum. So yes,
right.
The existence of other things, but I think also that there's lots of other things. Yes. Those principles, all these laws that we come up with now, and I think one of the things that Einstein said that really, from a philosophical point of view, I like, is that we really don't have the right law or the best description of the law until we get it to the point where the continuum of change can't change. Where we say it in a way that no matter what happens. So now I ask you a question about this backwards. So we're supposed to, the speed of something isn't supposed to be relative based upon, the continuum of change. But we have photons that leave the sun at the speed of light. And so from the point of view of the sun, the photon is leaving at the speed of light. Now, I think Einstein said that we should be able to look at the reality from any point of view. So what if we took the point of view of the photon? Wouldn't that make the sun be leaving it at the speed of light? I understand that the equations don't deal with it that way, because that's an enormous amount of mass moving at the speed of light away from a photon. But
yeah,
it seemed to be, yeah.
Yes, I think that it's hard to take the perspective of the photon, because the photon is sort of, yeah. That's actually a good one. You actually got me tied up on that one. Let me let that one rest in my head offline, right, and let's continue the conversation. And maybe, that's a very good question, actually. But just to be clear, what you're saying is that the sun emits light. Okay, and light gets to us at some distance d, and so from the perspective of the light leaving. Does it appear that the sun is moving away? And so the naive answer in the context of special relativity, right? what's going on here is that, in all frames of reference, the photon is moving at the same speed.
Right.
So even if you go into the reference frame of the photon, it's also moving at the speed of light.
Mm-hmm.
So you have to take into account basically the fact that the sun actually, general relativity, which is that the sun is warping space-time, and the photon is actually moving out of a gravitational potential at the speed of light. And there's a redshifting effect going on. So that's why I need to step back a little bit and couch it now, not in special relativity, because you're going to hit a paradox, which you just hit on, and deal with the question at the level of GR.
Right. And that's how we solve the paradox. But it's a fascinating thing because to me, because of that, and we won't go into any more detail on it, it sort of indicates that there's something about this that is hard to make universal. We know that there's something about relativity that's hard to match with quantum mechanics and their thing, but it's hard to say, okay, we're getting really close here, but there's something a little bit off because we can't really just make it universal by taking any point of view in the way that we've expressed our law. So, so let's go, and then superpositioning, isn't that a quantum mechanics idea?
Yes.
So that's another one of your big ones.
Right. So there are three principles that I based the book on to get us out of the jungle of countless equations and say, let's liberate ourselves from jargon and equations and get to the heart of the matter. And superposition is one of them. And that is it underlies quantum mechanics. That was a hard one because I had to figure out what, if anything, are there any fundamental principles in quantum mechanics? And it was really hard to pin down one principle behind quantum mechanics. But I had to surrender to one. And so superposition was the one. And that was mainly based on Paul Dirac, one of the architects of quantum mechanics and quantum field theory. And he wrote a book about, the foundations of quantum mechanics. And he begins his book with the superposition principle. So I stole it from him as the principle. And the reason why is because it's a place where quantum mechanics, this superposition principle is where quantum mechanics departs from our ordinary classical or non-quantum world. One way I like to say it is it's as if like, okay, in classical mechanics, the non-quantum world, if I throw allow me to say a football and be American centric, I mean by, American football, the oval one. If I throw away my right hand, right, the ball is spinning and moving towards you. So if I throw it towards you, it spins and moves towards you. So it's, it has a given state, we call it a state, that's unique, meaning that it's spinning and moving in a unique trajectory towards you, right? Or I can have a different state, which is I can throw it with my left hand and imagine it moves the exact same straight line toward you, but it's now spinning in the opposite direction. In the classical world, you will see either this or that, right? That's classical mechanics. That's the world we experience and live in, at least the one I experience and live in. Okay. I'm sure some of our friends out in Berkeley will beg to differ. No, but in the quantum world is basically states as a principle and as something that must happen, that both situations, both states, as I told you, have to be superposed. They need to be added together to actually make sense out of the experiments we see in quantum mechanics. So the superposition principle tells you that what are thought to be unique states of motion or states of existence that can only happen once at a time, in quantum mechanics, they need to happen all at a time. All those possible states need to be added up or superposed in that sense. And so that is weird, but that is what Richard Feynman, amongst others, told us has to happen at least at the level of the mathematics so that quantum mechanics can agree with experiments.
Yeah.
And then you
that's
talk about
also, I think,
ontology, then it becomes weird. Yeah.
yeah, I think that one of the effects of that is this idea that there's multi-universes everywhere, that they all exist at the same
Right.
time, right?
Right.
So for those of you who are fascinated by that, because
If you include yourself in the superposition state, yeah.
you're right, exactly. You want to live your life differently, some other location at the same time. It's appealing, but that's a little bit like time travel. It's appealing because we don't want to be responsible.
Right, exactly.
Emotionally. So it's a very interesting thing because that superposition idea is based upon the idea that we make the probability wave function collapse when we perceive an event, right?
Yes.
Okay, so what is the perception that's involved there? Is it a mechanical perception, or is it just our vision? I mean, what does it take to make something be seen? Because we do it with machines, really. And then there's this whole other question that you get into later, which we'll get back to about the universe. But what is it meant by that we perceive it in this in that quantum position? Nobody knows.
I've been asking the same question. Nobody knows. I mean, let me just give it a little. So normally what people like Niels Bohr meant was a classical measuring apparatus. So some device that does the measurement, and it's not us. So there's some device that's looking at this quantum system and tries to look at what the electron is doing to realize that the active measuring means that a device has to emit a photon, which interacts with the electron, then changes its state, and then collapses the wave function. And then you can then get more clever about it and say, well, let's do it in a way where it doesn't really collapse the wave function and da-da-da. But then there's still this issue that the electrons exist in a superposition of states. It can be here, it can be there. And then when I go and measure it, it's there. So,
right.
And so it's interesting because, one of the greatest minds behind quantum mechanics, and I believe he's one of the fathers of computers, is von Neumann. Wrote a book, I think it's called The Mathematical Foundations of Quantum Mechanics. It's a very daunting book that I struggled through, but I had to read it to write this book. And he basically traced mathematically the chain of events that ultimately lead to a conscious observer that has to register in their, minds or consciousness or photons in the eye, whatever it is, that traces back to us being the culprit. And Eugene Wigner was another one that I think made similar conclusions. I'm just saying that if, some of the greatest mathematical minds in quantum mechanics pointed in this direction, that it's maybe perception or consciousness or words that we still don't, I don't understand. That's doing the job. And then some people say, no, there's no problem there. It's just quantum mechanics is actually incomplete. And once we figure out a way, maybe of figuring out how the theory itself does a collapse in, then there's no need for this issue, for this type of woo-woo, as they call it. Right.
It's a probability theory. And it's a little like if you think of probability theory in Las Vegas with 1,000 decks of cards, it can predict the overall outcome, but it doesn't say anything about each specific card being turned over.
Right.
And I think that's mathematically, it's absolutely beautiful. And it's also so effective, one of the most effective predicting tools we've had. One of the things I think from that is that we can conclude that there is no alternative to the action of all of the tiny particles that are involved in quantum theory, that they're not deciding as they go halfway across to go someplace else, because you can predict exactly with trillions of things going on. So that's why I think it works well. But again, we're out here trying to figure out our shared reality, and it seems that probability theory approach is not specific enough to help us sometimes with what's really going on. It just helps us predict outcomes at that level, which is what we're working on. So,
I tend to agree with that. One way I think of interrogating that is when you look at the double slit experiment. It may give you a probability that the electron can go here or go there, but once you start asking, what exactly is the electron doing when it encounters these two holes? Quantum mechanics the probability interpretation of quantum mechanics by definition doesn't tell you that.
Mhm.
But there are other alternative interpretations that do tell you that. And like, so either way, let's say the probability interpretation is weird because it then doesn't tell you what the electron does. And it just, puts its hands up and say, we have no idea what it's doing. We can tell you probabilistically what it's doing, but you still have this. You do have the thing that's weird is that
right? Yeah.
it tell you when it's done. And
Right.
the thing that's interesting is that actually, the Schrodinger equation, which actually contains the information of the probability, is actually a deterministic equation. It actually itself, tells you what the wave function is doing at this time and what it'll do at time 20, right? 20 seconds later, the equation will solve that, but it won't tell you what the individual electron is doing at a given time. That's interesting. But my point here is to say that there are other interpretations that doesn't change the structure of quantum mechanics, the mathematics, that will tell you what it's doing at the expense of something weird happening. So my point is that either way I look at it, quantum mechanics is just weird. The other one tells you that you need non-locality, for example.
Right.
Spooky action at a distance needs to happen. And if you believe in that, then it will tell you what the electron is doing, actually.
Yeah.
But the electron is doing something because it knows something further on down the way,
It seems interesting too that those as they say, virtual quantum particles coming into existence and disappearing, coming into existence and disappearing. It would seem that that's a little bit against the second law of thermodynamics. That basically, or not that so much, not second law of thermodynamics, but the fact that there's conservation of mass energy. If we're supposed to have a certain amount of mass energy, then there should be a set number. I mean, I'm sure it's way in the decillions, but a set number of particles and a set amount of energy, all just changing all the time in the continuum of change. So it wouldn't seem that there would be any possibility of creation and destruction at moments that the quantum theory sometimes talks about because it fits the math of this fluctuations.
Yeah, there is. We physicists in the past did have to encounter this issue point of the conservation of mass energy.
Yeah.
And this is why, for example, the antiparticle was invented. So you'll have to tell me more about why this isn't, because this is a different situation. You're talking about non-locality. And
no, I was just talking about just the general idea that if you can have virtual particles that appear and disintegrate before they actually become real, then you seem to be talking about things, you're not talking about a set amount of anything, you're talking about a certain amount of random fluctuation. Some people like that idea because they think it allows for free will, which I think is kind of interesting. But
no, in that level, yes, I agree. Yeah. Yes. So, it's interesting. So quantum mechanics does tell you actually for that little instant of time, that little tiny minuscule change in infinitesimal change in time, that actually energy is not conserved. Yes. Right. So energy is energy conservation. So overall, if I look, the gross, it all conspires to cancel all of the tiny little violations in the conservation of energy on shorter timescales, conspires to give you conservation of energy classically.
Mm-hmm. Right. In the end, it gives you the right answer.
In the end, it gives you the right answer magically. Yeah.
And it's been so effective that it's kind of hard to argue against it sometimes, but it's still an area that some of the ideas about when relativity looks at something a certain way, it's not possible for quantum mechanics and relativity to both be right at the same time. And everyone knows about that. But let's talk about your third principle now. Okay. So yes, the third principle is emergence. Something that a lot of people talk about in a lot of areas outside of physics. But why don't you talk about what it means in physics?
Yeah, okay. For me, the simplest idea is when, water vapor becomes liquid water. Mm-hmm. So in other words, if you look actually, you take a little chunk of this water vapor and you look at it and say, okay, I interrogate what it's made up of. You realize, oh, it's made up of water molecules. Then when you look at the liquid water, forgetting about how it's organized, okay? Right. It's made up of the same exact water molecules, okay? So the individual water molecules themselves in the gaseous state and in the liquid state, the individual ones do not have the properties of the gaseous phase nor the liquid phase. Yet collectively, now this is, if you want to call it a swarm effect, collectively they swarm in a way to have the properties of a gas, right? So it has pressure, it has, it occupies volume in a certain way. It might even have a given temperature, right? All these things that gases will have. But the individual things, if you look at one, it doesn't have that property. And the liquid phase, again, what individual doesn't, it doesn't have fluid properties or fluid flow and vorticity, whatever the fluid might have, right? But yet it conspires collectively to have this emergent property. So emergence in this case is that the individual constituents, the building blocks themselves, can come together collectively to create properties that individually they do not possess. And so there are many examples. And so because we see this type of emergence happening regardless of the substance. So it can be quarks, for example. A bunch of quarks could come together to form neutrons, and then neutrons, under the right conditions, can form a superfluid state, which can be part of a neutron star. But we see superfluids going on with helium, right? Helium, molecules. Helium atoms. So we see these emergent properties happening regardless of the players in the game here. And so that to me made me say that and this was actually my way of, if I'm going to talk about modern physics in this book and talk about the frontiers of the field and what we're stuck on, I had to basically deal with the issue of reductionism. That simply by reducing our physical world to individual atoms and going to deeper levels and to smaller distance scales and discovering more symmetries and all this stuff, I had to realize that, listen, this is Philip Anderson, right? More is different, this famous essay. That basically, no, I mean, like there are things that we may consider to be fundamental properties that emerge, that they're not reducible to some building block, right? And so I wanted to basically state that emergence is a fundamental principle of the world.
Yeah.
Amongst the three other, put it at the same status of these two things that reek of basically seeming reductionists. Yeah.
Right. That everything is determined. Yeah. It's a very interesting part of modern physics because, before we were looking at things with what we can see. We only see a small range of light, that our photons bouncing off things. And there's a tremendous amount of other stuff going on besides that. And as we keep opening up to more and more things that we just didn't normally see, but we can see with our new instruments and everything, and we can tell that you could ignore the Earth altogether in describing what's going on. And you could just talk about the neutrinos that are going through it all the time and not affecting the Earth at all. But at the same time, the Earth is obviously an emergent property from what you were just saying. And it's so many combinations of so many different things in such a way that we have now been able to have life on it. But it's a fascinating sort of topic because this is where I wanted to go with the second law of thermodynamics. Entropy is the way that all of those small particles are moving, but something is pushing them in the opposite direction. Locally, not on a major scale, just like you said before, but locally, something is pushing them in the opposite direction. Now, when it pushes in the opposite direction, it still creates more entropy, which is according to the rule, but in that locality. So why don't you talk about that a little bit? You mentioned that, and it's kind of a very about the only way to explain what's going on. But and people, of course, love that for coming up with all kinds of different explanations for what causes that. But from a scientific point of view, this anti-entropic force, basically, at least locally.
Yes. Well, I mean, one thing that if I want to say, I mean, when we think about order and structure, like, the fact that, if I form, crystals, there is something that's causing that order to occur. Well, one thing that's, that's causing that to occur is that I am taking heat out of that system, right? That's one thing that, there's a flow of heat out of the system. And as things cool down, then what happens is that these atoms actually can now feel and smell out their local interactions and form bonds, for example. And, bonds then can maybe say something about the organizational properties, meaning it forms a nice little crystal lattice like sodium chloride and you get salt, right? And heat basically is agitation and the thermal random motions. So heat is synonymous with that or equivalent to that, the velocity. So if I slow things down now, I can see that you're here and you're here. Okay, let's form a bond. Now, so that's one interesting thing. So what's at work there is, of course, energy, right? And potential energy. So, so there is, energy that can go into a system that can cause it to basically form ordered states, so there's this real dance between like energy and one thing we take for granted, you need space. Give me some space, I need to find my own room. If you don't have space so that these structures could form within, and that's actually a big mystery as far as I'm concerned, because in the universe, actually, there is this dance where the universe started off like, very hot. And it reached a point where actually it was almost in complete perfect thermal equilibrium. We call this time the cosmic microwave background radiation. I mean, it's a time of equal matter and radiation where the universe was in equal forms of matter. Is very hot, very, everything was basically like similar to everything else. I mean, it's one way of putting it, right? So you're in equilibrium. So everything had the same property on average as everything else. All the atoms were moving at the same average velocities. And it's kind of, for all intents and purposes, formless and chaotic, right? And the temperature is on average the same, roughly 3,000 degrees above absolute zero, similar to the surface temperature of the sun. And it's, whenever you have a situation that is near perfect, in near perfect equilibrium, that's actually where the entropy, according to thermodynamics, is maximum. So you've reached the highest entropy state, the state of highest disorder. But it's interesting that because the universe, so you say that's then if the second law of thermodynamics says that systems will always tend to just move to a state of maximum entropy. Well, there you got it. In the universe's past, it was already there. So how did it end up in a situation where there's life? So the entropy certainly did not continue to grow. But what ended up happening is, luckily, because the universe is expanding and more space is being created, I'm using that word poetically, right? It turns out that now there's a situation where the system could cool. These high entropy systems can cool because there's space and gravity. So now gravity, which is creating this expansion, but also attracting the stuff. And then you form stars. Oh, how nice, you form stars. These stars are actually become lower entropy regimes, right? And so it's interesting now because these stars now, they can trap and coalesce energy through nuclear fusion to then create lower entropy systems and feed energy into those low entropy systems called biospheres and planets. So it's a very interesting dance, and I find that dance quite mysterious. And if you believe in a second law of thermodynamics and you think about it cosmically, there to me still is this puzzle, which is, entropy is still growing as because there's more space, but somehow it creates a situation where you can have islands of lower entropy. And that starts looking like, another system that does that are living systems. So it's almost as if like the universe is like a precursor to what living systems become. Or start behaving like,
behave with the same basic principle.
Yeah.
Well,
Schrodinger call it negentropy. Me and Salvador biologist Almagro Moreno call it the anthropocentric principle.
Anthropocentric principle. It's certainly got to be one of the biggest questions of the 21st century, in my opinion, about how we're going to put our physics together with our biology.
Speaking of which, that was really came out from a conversation I had many years ago. I was going on a spring day walk with Roger Penrose when I was at Penn State. And I asked him, we were talking about black hole entropy, and then he looked at me and goes, well, listen, I really, I have no idea what entropy is in terms of gravity. But this was one of the people, right? And so that got my head spinning. If Roger doesn't understand it, then I certainly don't understand it. and I still don't.
Now you're in good company. So you, before we get to the Q&A, which there's several coming in, you talk in your book about the principle of blackness in the universe. When you come to the next part of it, you title it "Fear of a Black Universe." You want to explain that idea a little bit?
Yeah, it is definitely an anthropic type of principle, anthropomorphic principle, meaning that if at the end of the day the universe created, we are a byproduct, we are one of the products, and so we are also subject to universal laws. And so the principle of blackness was something that was a play on words, and including my title, meant to be coy, but I would say the principle of blackness is basically the importance of embracing stigma, the importance in the evolution of scientific thought, and in the evolution, I think, of human societies, and also my own evolution as a Black man in America, was to, in writing this book and in navigating my career and my life, was to come to terms and maybe come to some peace with just embracing the stigma, embracing the fact that, that Blackness, being Black in America, does come with some stigma, being, people holding their books, their purses when I'm in the elevator, crossing the street, or being pulled over, or not being taken seriously intellectually, in amongst certain colleagues, not all, by the way, that actually, and that actually there's a beauty to that. Actually, it doesn't feel good, and it's inconvenient and dangerous sometimes. But also seeing it from a more broader perspective, that when in researching for my book, I discovered that this state of stigma of being ostracized, kicked out of the club, not funded, not promoted, not getting a job, simply because, let's say, in some cases, the idea you had at that time in that context of history was deemed to be worthy of being shunned or stigmatized. So when Faraday, who came from a working class background in England, is theorizing about invisible lines of force, how witchcraft is that, how uneducated is that, to have this crazy idea of invisible lines of force. It was laughable. He was, historians of science say he died heartbroken because it was never accepted, and people, his peers said it was idiotic. That sounds very similar to people today who may talk about, similar ideas, and they're made the laughing stock. And so the idea of Blackness, the principle of Blackness, that sometimes we need to embrace that. We need to also sometimes invite that. It doesn't get you away, by the way, from knowing your physics and doing the work. And I'm no way saying that, hey, everybody just come. No, I'm saying that, on top of that, we should welcome and expect the Black ideas, the ideas that might be crazy, because history has shown us that some of the great ideas and that advanced science and physics were those ideas. And so the last thing I want to say about that, to bring it back to the personal and the sociological, was that one of the things I really was hoping to get out of the book was to not yet be a book saying, "Oh, woe is me, I'm a Black physicist and people have treated me this." My book, it was really meant to say, to acknowledge that and to inspire younger people and prepare them to have a certain realistic expectations. But to celebrate, to actually say, I'm proud of that. Actually, I think it's really cool.
Mm-hmm.
I want to be like Coltrane. I want to be that like Coltrane, who's like who can play giant steps, but could bring in a Pharoah Sanders and an Ornette Coleman and learn from that, right? So
Right.
the book was a celebration of the outsider, the celebration of the Black ideas.
Yeah, and it was a successful celebration of it. One of the charms of the book is that. And as you said, if you look at the history of science, almost everybody was stigmatized when they came up with any ideas, and it takes a long time, even on really mundane things. But Socrates was certainly stigmatized as
that's a real one.
Yeah, that kind of thing. So I think, like you said, if you're getting stigmatized, I mean, it might be for the wrong reasons, but if you're doing the right thing, it could easily be for that. I think more people have been stigmatized in human history for doing the right thing than for doing the wrong thing. Everybody identifies with the wrong thing.
Right. Thanks.
But very few people identify with doing physics and trying to figure these things out. So I thought that was a great point in your book. That's why I wanted you to talk about it, and you did a great, passionate job of explaining it. That's why I started with the diverse idea too, because, like you said, there's questions about all the big theories that we have now, and we need as many people who are interested in that from as many points of view to come along and say, hey, I see this thing over here, and other people might not be aware of that because they didn't get raised that way or whatever, and we get insights from all over the place, and it might not be the final insight, but it might be the pickaxe in the wall that rips the wall down, and
that's right. And that's why we do it collectively. That's right. So we have to rely on some people to put out those ideas. And then, it's like a baseball team or whatever. Your job is to do this. Well, my job is to do the crazy idea. Right.
Yeah. If we can not kick out the people who come up with, that all the multiverses are going on all at the same time, it might look good mathematically, but it doesn't seem to be a likely answer to our problems. So we can accept, all kinds of ideas have been accepted to use to try to figure out what's going on. A lot of the times what they're useful for is showing what's wrong with the mathematics.
Right.
Then you can say, well, if this is the conclusion of the mathematics, we must have gone astray someplace, that kind of thing.
And that's right. And one of the things I try to really pin down in the book is that while mathematics is one of my demigods, it's a tool. The intuition reigns supreme. It's, our mind is not a math equation. Okay. We generate ideas and intuitions, and math is powerful. And it's its own universe, and it's a very powerful tool, but we have other colors or tools in our palettes that we should explore and expand upon.
Yeah.
Yeah.
Almost all advances have been intuitional, but what makes them advances is if you can support them with mathematics and logic and internal consistency, external consistency. A lot of it is clear thinking, clear conceptual thinking, and then the math can demonstrate it. But one thing's a lot of people, they think of math and they say, well, it proves things, but there's some proofs in math, but it doesn't prove the theories. It's just, it's more and more consistent, and therefore we have more reason to rely on it. People say, well, you believe in reason. Well, no, you shouldn't be believing in reason. You should be relying on it. And that way,
I like that.
When you have another better reason, you rely on that because it's a better reason.
Right. I like
instead
that.
of believing in something. Yeah. So we have a couple of questions. I'm going to get back to my big question for you after I get through the questions from our audience.
Oh God, well, I'm scared.
So first question, has string theory advanced much in the last few decades?
I think on one level, it depends on what, I think it has advanced in terms of like addressing some of the questions that I'm interested in. It hasn't advanced enough. But I think it has advanced, and I think, string theorists are the people that work on string theory, some of which are friends. I think what they're doing is very well motivated. And, when you put things in perspective, it's amazing that string theory has advanced as far as it has. In the eye of like human, the thousands of years it took us to get as far as we did. So that's my short answer.
All right. And I'd like to mention that Wonderfest as an organization has helped support this lecture. And I'm sure some of these intelligent questions are coming from people that belong to Wonderfest because they always do this for our physics things. So the question 2, is dark matter likely to be atomic, molecular, and some minute dust particles?
Well, I definitely have some colleagues in the astronomy in the astronomy world that would like so, but I would say the answer is from me, no, because we see the evidence of dark matter, the need for dark matter, before we even knew about, we saw it at the level of the cosmic microwave background radiation, where we realized that you needed an extra component that had exactly of roughly 25% of the energy density of the universe that had the properties of dark matter before we had dust particles exist in cosmic history.
Right.
All
right. And
but it doesn't mean that dust particles are not a component. Let me just clarify something. It doesn't. So one idea is this idea that dark matter has to be one and only one thing.
Right.
And it could be that dark matter actually may get contributions from different things, but you're probably still going to need, even when you account for things like, invisible, like stars that are, primordial black holes, things that you just can't see, but it still matter, right?
Right.
So you can add all those things up. And I guess my point is that you're still going to need something weird called dark matter that we don't know what it is yet.
And as you say in your book, there's a sort of a halo of dark matter around galaxies, but we don't see that. Obviously, that's why it's dark matter. We know that mathematically, isn't that correct?
Yeah, we infer that from the rotations of the motion of the visible matter.
Right.
That's right.
Okay.
And also gravitational lensing, the lensing effect, how light bends around these objects.
Yeah, it's interesting how many objects, if you just look at it conceptually, how many objects are mostly spherical with denser and denser cores and a little bit less coming all the way out, and it's just
yes.
But it's not a completely homogeneous spherical thing. There are different structures within it that are different, and so the idea that mathematically that the what we call spiral galaxies and everything have a relatively spherical overall thing that has dark matter to it makes sense along with all the other objects, because that's such a common form that the universe takes, or different parts of the universe takes.
That's right. And in fact, I put a paper, the paper just came out today online, published. It's published online, a paper with my former postdoc, Evan McDonough and David Spergel, where we actually literally showed the reason why that could happen. We have a model of dark matter that basically shows if you take a neutron star and the exact same physics of a neutron star, which is a superfluid of condensed neutrons, and claim that dark matter are invisible neutrons, meaning that they don't interact, they're dark neutrons, they don't interact directly with our neutrons, and then make it as large, right, as a halo, right? It's the same, that is dark matter. And the reason why it's circular, the same way it's spherical, it's the same reason. It's the same exact physics, just, again, an analogical reasoning. And the equations worked out quite nicely. So,
that's great. That just came out today.
Yeah, except it's a quantum fluid, so that's weird. So it goes against, I was thinking that quantum mechanics is only happening on microscopic scales. If you believe this, quantum mechanics is on a scale much larger than a galaxy.
Yeah. Well, now here's a question pretty hard to answer: is space infinite in the universe?
I don't know.
We'll refer you to Albert Einstein on that one. Yeah. Please share your next question. Please share your thoughts about what happened before the Big Bang and how the universe makes consciousness possible. So before the Big Bang, you had Stephen Hawking say it doesn't make any sense to ask that question, which I found interesting. But go ahead. Before the Big Bang.
Yeah. Yes, before the Big Bang. Yes, before the Big Bang. Let's see. Before the Big Bang, you have to go to a place where there is no space. And in my picture, the time has to be running still. So I have to have something. So time, the the situation where you can have things changing, even though there's no space, is my starting point. And the idea that there is that, in quantum mechanics, we learned that you can't really talk about a particle unless you talk about a wave. They're both needed to talk about each other. It's called complementarity, or the yin and the yang, okay? You can't have one without the other. So the reason why then, good. So the reason why you see a particle, right, is because you have made the idea of the wave fuzzy. You've made it completely, right? And vice versa, right? So if you think about a particle as an analogy now, a particle is by definition something that's localizable. It is located at a given point or a locus of points in space. Yeah. And if I think about something like a wave, it's extended everywhere. By definition, a wave is everywhere. If I take especially a perfectly periodic wave, where is the wave? Well, if one peak is the same as another peak, there's no unique peak. So the wave is everywhere. So in a sense, the trade-off is locality versus non-locality. But you need both. And they compromise each other. If you are in a situation where you're seeing this, is because you have compromised the wave-like property and vice versa. So imagine that there was a situation in our early universe where you have compromised space or the localizability of space relative to something in space with the act of observing, localizing. And so one of the things I tried to do in this picture, and had to do with Schrodinger, and I go into a lot of details in that last chapter that I don't think I can reproduce in a few sentences. But by using this idea of saying that if I give up the idea of space and think about consciousness, okay, and again, in a way that where I now think about, again, in every physical theory, we have to have a beginning, an axiom, an assumption. So the assumption here is panpsychism, is that for every substance, every bit of physical reality, there is some proto-consciousness, not our consciousness, not an ant's consciousness, not an electron's consciousness, but some internal experience of the object itself. That right? So it is bit. And for it to exist as a physical entity, there has to be some quality associated with that. And this is not my idea. This idea goes way back actually to to ancient cultures. And now it's but great neuroscientists like Christoph Koch and others have been rethinking panpsychism. But what I'm going to ascribe to panpsychism is space itself. Okay, so there's a sense in which if space exists, there's consciousness associated with that space. And the idea is that, but it's not in a sense of that space is. So if you have that, then the idea now of the universe basically. So there's an idea now of complementarity at work. So we have space, but then we have events in space that are localizable, right? And so the idea here is that what's localizable is actually that consciousness becomes non-local, whatever that is. I'm not that, you're not that, because our consciousness, one assumption that we're making is that we are perceiving things and taking the information and are self-aware of us being localized as a body in space. We take that for granted. But imagine if your body was the entire size, then what's your consciousness, right? It's non-local. So the idea is that somehow that there's a complementarity like wave and particle, local, non-local, as this space, the universe basically existing in this thing. And what's quantum there, because we have to talk about quantum space-time, is that somehow that localized observers now localize events. So in this case, the universe basically goes from this, that's a pre-Big Bang state, that what is going to become space has to basically become a non-local situation first, so that space can occupy everything. But then, later on, once that happens, somehow that non-local consciousness has to become localized. And that is basically where we start seeing events like, the collapse of the wave function of the universe, because you don't have other observers out there to collapse the wave function. So again, it makes certain assumptions. That's the idea. But in a nutshell, I probably did a very bad job. So therefore, one has to go and read the last chapter of the book. But the point about that chapter is actually not that I cared I was right or wrong. Mm-hmm. It was really me deliberately engaging in Black thinking. I really just set that up so that I can be speculative. I gave myself the permission to speculate without caring too much about if people think I'm crazy or not, or worthy of being a physics professor or what have you. It was, I wanted to have fun, and that was my way of doing it. I always wanted to do it, and I finally gave myself permission to do it. And well, it makes no sense, but.
As you said, theorizing never killed anyone. I'm not sure Socrates would agree with that, because it did kill him, but right. Theorizing is, as you said before, it's, even if it's a wild theory, but no matter what the theory is about consciousness, we have, as you put in your book, we have the hard problem of consciousness. It's not going away. It's there. We have to, if we're going to explain our reality, certainly we have to explain why we're even able to discuss these ideas at all. So now that is an hour's conversation all by itself. And we have, a few minutes left here. I want to move to another hard problem of consciousness. You talked about Deepak and some of the ideas from Deepak Chopra, that is, and some of the ideas that he has. I want to propose that there's a hard problem about Brahman consciousness or cosmic consciousness, or these other ideas that people talk about to try to explain the universe. And the problem is this: if you say that the universe started with this oneness, this one mind, and then you say that it sort of fragmented itself into all these quadrillions of minds, in a way you can say, and then the purpose of all those minds is to get back to being one with the oneness again. Then you have a big question, which is why? Why was that done? Why was it fragmented? And is it presumptuous of us, if the one mind expelled us or fragmented us all, is it presumptuous of us to try to get back into it? Because if everybody succeeded, we'd be right back where it started and have to do it again. And there is no conceptual logic, to that part of the equation. There's a lot of appeal over the long period of time, and there's a lot of experiences by yogis and so on that points in this direction. But as somebody said, whenever we're discussing big issues like that, we're like, two fetuses in a womb trying to explain reality. We have so little experience, and it's interesting that modern science has given us many more experiences, because people die and then they are brought back, and there's a lot more people talking about it. But one of the things that's most common about those experiences that they say, I felt I understood everything, but they don't come and solve physics problems for us.
Yeah.
And if they did understand everything, they should have been able to.
Yeah, no, it's interesting. I mean, I think that I'm very attracted to the idea that there's one mind. In fact, in a lot of ways, that last chapter of my book, I was exploring that thing and trying to reconcile that with what we know about cosmology. That's kind of what I was trying to do there. Was like, okay, let's assume this is one mind. How do we talk about one mind in the context of the Hartle-Hawking proposal, the wave function, and using panpsychism? What can I bake out of this theoretically to be consistent, whatever, right? That was the game I was playing. And I agree that there's a paradox. There's a paradox, which is unless they're both operating at the same time, right? In some way that, this idea of like, what's the, you're looking at something, but if you're looking at it from a different perspective, you see something completely different. Right. But the thing itself contains all perspectives at the same time. And maybe like nothing ever really happened. Nothing ever happened in the universe. But we're like, whoever we are seeing it from the perspective that something has happened and we are separate, and that'll be a beautiful idea. But okay, what's the rotation that we need to make in this thing to be able to see the other perspective, huh?
The invariance principle, and then if superposition could put both of those things on at the same time, then quantum mechanics would solve another problem that it's not expecting to.
Well, good. I'm glad you brought that up. Let's say that I forgot to say that Schrodinger, in his book, What is Life? The book was actually, my book was a play on trying to answer and expand on those questions. Because remember, he kind of almost created biophysics by asking these questions, by speculating in this way. You know, he talked about negentropy and he talked about DNA. He was able to almost guess the structure of DNA just by this kind of thinking, and actually being, he was being, what's the word? Like when you're interloping in other people's field, like, right. You don't know the stuff, and boom, Linus Pauling sees us, and Watson and Crick and Franklin. And the point here is that one of the last questions he left that nobody picked up on, and I did, was he asked this question: why are there so many minds in the world?
Right.
And so I started thinking, oh, that's interesting, because the same way, you think that there are many, waves, but actually there's one particle. But you need these many waves to talk about this one particle. That's complementarity. So that's exactly why I came in with this idea to say, Schrodinger, maybe the answer is there's really one mind, and there's a perspective that's non-local in the same, by using the same analogy. And what appears to be these many minds are just basically a complementarity perspective on the one mind. They're complementary to each other. And therefore, but how that happens and what's the mechanism and what's its wave function, again, I'll leave that for somebody else to speculate on.
Well, the bottom line, though, and I figured it would be your bottom line too, is that we should encourage interlopers, people who are really good in one field. And you can't ever learn all the details or all the math, but you can think about the conceptions, because the conceptual thinking that's behind Einstein's work, he's written about, and he makes it fairly clear what he was thinking about. And even if you don't do the math, you can still think, well, what about this idea versus this idea? And so I think, I'm sure you agree with me. Interlopers.
Thank goodness for Marcel Grossman, right?
Yeah, absolutely.
Yeah.
Everybody should, somebody's got to be specialist in our specialist society. And that's where, you make the most progress. But helping everybody else think about things, you should be an interloper some of the time and throw ideas out that seem.
I like that idea. We should definitely, and that's interesting, right? Because a lot of us don't embrace the interlopers.
Right.
We somehow feel threatened. I don't know what it is. Feel threatened. It's not in our club. This is a very human thing, right?
Yeah. Well, you don't want someone who hasn't studied it for 50 years to come up with an answer that you didn't. That's one reason. That's one reason. But there are other reasons. But the fact is, it's been done many times before. And if you study the history of science, you'll know that it'll be done again. And because we're so specialized in the 20th century, we don't have as many people looking at the big picture. So I like it from a philosophical point of view for as many interlopers as possible to come out and say, well, what about this? What about that? And all you have to do is be modest about it, not say you're wrong. Just say, what about this? Think about this. That's all. So
are you saying you're going to form the Hammond Interloper Institute?
I would never try to organize that group of people. It's not an organizable group of people. Everybody can do that independently. That's just fine. Oh, that's a great end, Stefan. Good idea. So ends another event at the Commonwealth Club in its 119th year of enlightened discussion. Thank you so much, Stefan, for engaging in that conversation. That was wonderful.
Yeah, thank you so much for having me.